Welcome to video 3.2. In this video, we'll be talking about understanding charge using pKa, probably one of the most important skills and difficult things to do in biochemistry, and specifically in regards to protein. By the end of this video, you'll have a strong idea about how to intuitively understand the relationship between pH and pKa for the N and C terminus of amino acids. As we discussed in the last video, at pH 7, the amino acid or amino acid chains exist as a zwitterion, where the N terminus has a positive charge and the C terminus has a negative charge. Now, I'm going to define this term ionizable, which basically means can gain a charge. So, ionizable groups can gain or lose charge. Right? A group that is not ionizable is going to always stay the same. Peptide bonds, which are, for example, in this area here, are going to be non-ionizable. Right? Now, technically, anything is ionizable with enough energy, but in the context of everyday biochemistry, this group is never going to gain a charge. The backbone of the protein will not gain a charge. The N-terminus is ionizable. Right? We talk about the NH2 group reacting to make NH3. And it needs to get an H from somewhere, like an acid. So this hydrogen becomes the third hydrogen of NH3. That is an ionizable group. It can gain a charge, and specifically a positive charge. The C terminus, a carboxylic acid, is also capable of gaining a charge, but not by gaining a positive charge, but instead gaining a negative charge. It loses its hydrogen to some sort of base. And it is ionizable by getting a negative charge. So first thing to note, and I'll come back to this, N-terminus will never be negative, C-terminus will never be positive. That is true for these functional groups. The side chains, it depends. Right, so now we're talking about the R groups, R1 and R2, for example, in this example. It depends. Some do and some don't, and we'll be diving into the amino acids in the next video. Importantly, you're going to need to know the structures of those amino acids and their functional groups to be able to understand their ionizability. With that, let's keep moving and understand the best tool to predict this charge, right? I said at pH 7, it'll be positive, but what about other pHs? So the best tool to predict charge is pH and pKa. The equation for pH is the negative log of the concentration of hydrogen. If we think about the general acid equation, HA, some sort of acid. So in this case, for example, we can imagine this being the carboxylic acid, right, where H is this hydrogen and A is the rest of the carboxylic acid, reacts with water and produces this plus H plus, or H3O. I'm just going to put H plus here. As this acid loses its hydrogen, it provides H to the environment. And it's this concentration of positive H, or hydrogen, that goes into this equation here, right? So if we think about how this term works, pH, when the concentration of the H is very high, that means we're talking very acidic. What the pH term does, the negative log term, is we actually see a very small pH, right? And low pH is acidic. So it's important to remember how that negative log, so the P here is negative log, so negative log H, that negative log takes big numbers and makes them small. Alternatively, when the concentration of H is very low, the pH becomes high. And I want to make sure we understand this ionization with a specific key concept. And let me just get rid of this group here. Right? The concept is that atoms turn into ions by gaining or losing hydrogen. Right? We're going to really focus on pH and pKa really as our big guideposts here. So if we look at the N-terminus, for example, it can gain a hydrogen and become NH3+. But to do that, it needs a hydrogen, right? The C-terminus can lose its hydrogen, as I mentioned above. And so when we think about ions, we think about charges forming, we should be thinking about hydrogen being given makes positive, hydrogen being taken away makes negative. That's not universally true, as we'll see, and we'll do more examples in the same video. But for now, that's what we're really focusing on, is understanding when these are going to be positive and negative. So what is pKa? Right? The idea is that every ionizable group or an acid has some sort of HA and A form, right? So if we're thinking about the general acid equation, there is some acid form, and it reacts and we make A minus. If we have the acid form, the pKa is going to be a constant for that acid. So every acid, for example, NH3 or NH2, right, the pKa's of the group, we're going to get an idea for how strong that acid is. Same idea, it's the negative log of Ka. Ka is how strong the acid is. So a low pKa means high acid strength, and that's really all you need to know about pKa for this. So for example, if we look at amines, right, we can see there's one form that has a hydrogen and another that is missing that hydrogen. So I could assign this the HA form and this the A form. Keep in mind that A will not always be negative and HA will not always be positive. In this case, the HA form, the form that has the extra hydrogen, right? That's really what we're focusing on here. Extra hydrogen is positive, but the A form is neutral. Looking at other functional groups, like carboxylic acids, the A form is going to be negative, where the HA form is neutral. Right? The HA form has the extra hydrogen, the A form doesn't. For the thiols, same thing. The A form, in this case, is negative, doesn't have the hydrogen, here it does. I'd highly recommend memorizing these 4 cases. These are the only cases you're going to really run into. I mean, there are some exceptions to that, but these 4 are very handy. It's good to know that nitrogen is going to be positive when it's charged with the hydrogen, right? And everything else will be negative without the hydrogen. So with that overview covered, I kind of mentioned this already. There's 2 kinds of ionizable groups. The neutral acid is an acid that is neutral in its HA form. So for example, the carboxylic acid, right? When you take away its hydrogen, it turns negative, right? But at the end of the day, it's still an HA and an A form. I want you to really keep that in mind. For the positive acid, this is something like NH3+, right? NH3+ is the HA form that turns into NH2, the A form, right? The A form in this case is neutral. I call this the positive acid because the acid in its A form has a positive charge. But regardless, it's important to recognize what is the HA form and the A form for these functional groups. You'll see how this is really crucial as we move on. Now, the Henderson-Hasselbalch equation is really the big missing piece here. It's going to link the pH of the solution and the pKa of the acid. And it makes it, we don't have to go into too much depth for biochemistry. There's more to dig into with this equation. But as a quick derivation, right, we have this idea that this is or not derivation, but this is just the equation, right? The pH of your solution is equal to the pKa of the acid plus the log of the A form, which is the less hydrogen form, and the HA form, the more hydrogen form. I'm using this terminology for a reason. I quickly wanted to show that by rearranging this equation, you can say, so subtracting pKa from both sides, pH minus pKa equals the log of A over HA. And this is an interesting question. What happens if pH is equal to pKa? Right, so let's say, for example, that I have, let me give you a discrete example here. The C terminus of a protein, if it has a pKa of 3, and again, the pKa, remember, is a constant value. It's a value that won't be changing. It's what the C terminus is, right? It's a constant. So if it has a pKa of 3, and I put it into a solution at pH 7, or a solution at pH 3, right? So let's do the bottom first. What happens if pH is equal to pKa? So let's look at this equation for the Henderson-Hasselbalch. pH is 3 minus the pKa is 3 means that we're looking at 0. So the log of A over HA must be equal to 0. Interesting. It turns out the only way to mathematically make this work is that A and HA both have to be the same number, because the log of 1 is equal to 0. So what this tells you is that when the pH and the pKa are equal, the concentration of HA and A minus, or not necessarily A minus, but HA and A, are the same. Which means that in this solution, if I had 100 molecules of my C-terminal, my carboxylic acid, half of them, I'd have 50 of them with the hydrogen and 50 of them without. Really important idea. Remember that this is where the equality comes in. It's 50-50. So now that we're looking at the carboxylic acid at pH 7, how does that change, right? We have the pH, which is 7, minus the pKa of 3. That equals 4. So now the log of A over HA has to equal 4. In order for that to make sense, the A value has to be much, much, much bigger than the HA value, right? That's kind of the math of like how logs work. So with that in mind, the A form is going to dominate, right? The A form of the carboxylic acid is actually the O minus. And that's what I said earlier. At pH 7, carboxylic acids aren't actually shown this way. They're shown with the negative charge. Only when they reach a pH of 3 or lower do we start seeing them in their neutral form. So that's how pH and pKa are related. And I want to do through a couple examples going through just that again, because it's a really intuitive pathway that I want to run you through, that if you understand this, it'll make a lot of the pKa stuff to come much easier. Let's start from the top. If pH is lower than pKa, right? And I guess, we can say, what is the question? That's probably the more important thing. I want to know the charge at pH 1 for the N-terminus and the C-terminus. To make this simpler, let's just do the N-terminus, because we already did the C-terminus. The charge at pH 1 for the N-terminus, given that the N-terminus has a pKa of 10. For this question, let's quickly think about what the N-terminus is. The neutral N-terminus has the NH2, and the HA form is NH3. So we have the HA form and the A form. We want to know these going in. If we don't know this, it's going to be a pretty challenging question. We'll get confused pretty easily. Now, charge is at pH 1, so we know that the pKa is bigger than the pH. Here's how I like to view it. If the pH is lower than the pKa, that tells you, right, remember that if pH is equal to pKa, you have a perfect 50-50 mix of HA and A, right? The amount of hydrogen around, which is what pH tells you, makes it a 50-50 mix. The pH is lower, though, which tells you that the concentration of hydrogen is high, right? There's lots of hydrogen around. And that, it's a little silly, but I like to view it that way. Lots of hydrogen around. Therefore, which form is going to dominate? Well, if there's lots of hydrogen around, right? Remember that if the pH was equal to pKa, these forms would be equal. But if there's extra hydrogen around, it only makes sense that HA will dominate. So if it's a neutral acid, the HA form is therefore the neutral form. And if it's a positive acid, the HA form is positive. For the N-terminus, the HA form is this one, right? The one with the extra hydrogen. So it makes sense that when there's more hydrogen around than would be at equilibrium, HA is favored. So the charge at pH 1 for the N-terminus is positive. Let's do the same thing, but at pH 14. Again, we need to know what that N-terminus is. We have our A form and we have our HA form. So if pH is greater than pKa, so pH is now 14, pKa of the N group is 10. So that means the concentration of hydrogen is very low, right? If the pH is high, that means the concentration of hydrogen is low. There's not very much around. So which of these two forms is going to dominate, right? Well, remember, again, I'm going to come back to this. If the pKa was 14 and the pH is 14, then these are equal, right? pKa and pH would be 50-50. Since the hydrogen is low, though, the pH is lower than the pKa, the A form is going to dominate. And in this case, we're dealing with a positive acid, right? The HA form is positive, A is neutral. But you can see that even without thinking about that, the A form, the one without the extra hydrogen, is the one that's going to dominate. So the N-terminus is going to have a charge of 0. With that in mind, this workflow of thinking about the pH and pKa relationship, saying, is there more or less hydrogen and which form will dominate, and then knowing what form you're talking about, that's an overall strategy for success when you're thinking about charge and pKa. Without further ado, in the next video, we'll start introducing the 20 amino acids, the key structures, and the key pKa's to commit to memory. I'll see you there.